Hello everyone, we are back again with class 12 physics. The chapter is wave optics and the topic today is diffraction. In the previous video we have finished interference and today we will start a new topic which is also very important with respect to board exams. Diffraction is the phenomenon of bending of light around the corners of an obstacle into the region of geometrical shadow of the obstacle. Basically what is happening here is that, like we studied in the previous classes, that light travels in a straight line. But diffraction is the phenomenon which is proving it otherwise. Because of diffraction we can see that light does not travel in a straight line but it bends. But the condition for bending is that the obstacle should be very thin, okay? Like the edges of a blade, a very thin obstacle. When you place a very thin obstacle, light going straight onto that obstacle bends into the geometrical shadow of that blade, suppose, of that obstacle. The diffraction shows that light does not have particle nature. It bends, it means it has wave nature. Okay? So let us write down the definition of diffraction, which is the phenomenon of bending of light around the corners of an obstacle into the region of geometric shadow of the obstacle. So this is diffraction. Now there are two types of diffraction. One is Fresnel diffraction and the other is Fraunhofer diffraction. Okay. In Fresnel diffraction, either the source of light or the screen or both, either the source of light or the screen or both are at finite distance from the obstacle. Okay. Suppose I have a slit where is an obstacle, so my source, either this is at finite distance or my screen on which I will find the image is at finite distance, or both are at finite distance. It cannot happen that the source as well as slit both are at infinite distance. So this type of diffraction is called Fresnel diffraction. So let us start with Fresnel diffraction. The first type of diffraction is Fresnel diffraction. In this type of diffraction, either the source or the screen or both, the source means source of light, both are at finite distance from the obstacle. Okay. The other type of diffraction is Fraunhofer diffraction. In Fraunhofer diffraction, the source and the screen both are at infinite distance from the obstacle. Now the question which arises is that if both are at infinite distance, how do we know that diffraction is occurring there? How do we find the image? So basically what we do, we use a convex lens. We use a convex lens to converge it, and then it meets at some point and we see that it is having diffraction. So we use convex lens to find the diffraction pattern in Fraunhofer diffraction. Okay. So the second one is Fraunhofer diffraction. So what happens here, in this type of diffraction, diffraction, the source as well as slit are at infinite distance from the obstacle. So if both are at infinite distance, I told that convex lens is used. So the light after diffraction is focused on the screen using convex lens. So these are the two types of diffractions which we have known now, out of which only Fraunhofer diffraction is of some importance to us, is of some importance in our syllabus. So when we deal with the next topic, which is diffraction of light at a single slit, we will be discussing about Fraunhofer diffraction. Okay, so let us move on to the next topic, which is diffraction at a single slit. So the topic is diffraction of light at a single slit. So let us start with the diagram for it. So we are considering that we have a source of light, and because it is not easy for us to make a source of light which is at infinity, we will use a convex lens here also. Okay. Suppose we have a source of light emitting light in all directions. I use a convex lens here. That convex lens forces the rays of light to go in only one direction, making a wavefront. This is the wavefront W dash, which is having a distance d. Distance between these two parts will be d by 2 and d by 2. If from my diagram it is not seeming, then you can try to make a better one. Now after it I have placed a slit. Here is a slit. Okay. So this is a perpendicular from slit. So we have a slit here, and I am taking the two points A and B here. If there were no slits, light would have gone to the next lens and then it would have merged to form a diffraction pattern at this point. Let me take this point as O. This O is the point of central maximum where there will be highest intensity will be there. Now, but because of this slit, the light tends to move in a different direction, changes the direction. Now, by the same angle at every point. This angle is theta. All of them will be theta, and then they will meet at a different position also. This angle is not seeming to be theta, lesser it is. Now, what will happen now? Oh, sorry. These rays will meet at different point P. Okay? After diffraction, these rays tend to meet at a different point, which is point P. Now, this P can be the position of a minima or the position of a maxima depending on the path difference, just like we discussed in interference also. But here the concept is a bit trickier. You have to be very focused to understand. Now, let me have one more point C here in the middle, and because of the change, I have to draw a perpendicular on this surface, name it N, AN. Correct? This is perpendicular, and so what do I get? I get that my path difference here, which is the difference between the AP and BP, is BN. This is the path difference. So Bn is the path difference, and its value will tell me if there is constructive or destructive interference, or if the diffraction pattern will be bright, or will it be dark, or will it be having maxima which is bright, or minima which is dark. Okay. So I have this path difference Bn. For constructive interference, that is for a bright fringe or for maxima. Now, let us first talk about destructive interference for minima. So what I am taking for minima, that this distance Bn is equal to, or the path difference is equal to only integral multiple of lambda. If it is suppose 1 lambda, then the path difference between this AC and BC, because they are half and half, will be lambda by 2 and lambda by 2. No? So a wave going from A to P and a wave going from B to P will be having a path difference of lambda by 2. That is destructive interference. But not only A to P and B to P. What happens? For every point here, there will be opposite point here, which will be having path difference lambda. Suppose this and this are having lambda by 2 path difference. So this and this again are having lambda by 2. This and this again are having lambda by 2. So for every point in the upper part, there will be a point in the lower part which will be just cancelling it, or for which the path difference will be lambda by 2. So basically this point P becomes a position of minima. Correct. So let us discuss the condition for minima. Firstly, we start with path difference. So we have path difference Bn is equal to, this is Bn, so that I am taking triangle ABN. When this is perpendicular and suppose this one is theta, this one is theta, similarly this will be theta. So in my triangle ABN, this is 90 degree, this is theta, so that means BN is perpendicular, AN is base and AB is my hypotenuse. Correct? So what do we get? BN upon AB is equal to sine theta, or Bn is equal to AB sine theta. I already have the value for AB, which is equal to WW dash, which is equal to D. So if I put AB to be D, I get here Bn is equal to D sine theta. This is the formula for path difference. Now the conditions for minima and maxima. Firstly, I am discussing about for minima. For minima, I am considering that the path difference Bn, which is equal to D sine theta, is an integral multiple of lambda. Is an integral multiple of lambda. So I am taking theta n here. So this means for the first minima, D sine theta is equal to lambda. For second minima, D sine theta is equal to 2 lambda. For third minima, D sine theta 3 is equal to 3 lambda. And so on. For nth lambda, D sine theta n is equal to n lambda, where n is equal to 1, 2, 3 and so on. So this is what I have for minima. The condition for minima will be, minima will be D sine theta is equal to n lambda. Okay. I am erasing Bn from here. For minima, D sine theta is equal to n lambda, because I have already told, if I take it to be lambda, for the upper half it is lambda by 2, for the lower half it is lambda by 2. Lambda by 2 and lambda by 2 always interfere here out of phase, so destructive interference, minima. Okay, if the angle theta is very small, let me first change it to sine theta n is equal to n lambda by d, and if angle is very small, if theta is very small, what do we have? Theta n equals to n lambda by d. If the angle is small, theta n equals n lambda by d. Now we talk about when will we get secondary maxima, because central maxima we already have at point O. No? At point O we have central maxima. Central maximum is the brightest point. Nothing else can have the same brightness as central maxima. But on both sides of central maximum we will have secondary maximum, which will be less bright but considerably brighter than the minima. So how I get a maxima? So for having a maxima, I am considering that my path difference is an odd multiple of lambda by 2. Just considering that my path difference is an odd multiple of lambda by 2. For example, 3 lambda by 2 or 5 lambda by 2, 7 lambda by 2. I am taking the example of 3 lambda by 2. For a path difference of 3 lambda by 2, we can divide our slit into 3 parts. Between any 2 points, we will have destructive interference. but the third point will also be added to this. So what is happening? Destructive interference between these two and between these two, but all are joining here. This means the intensity is less here, but when these two less one added here, increases to lesser amounts, going to same point, increasing in intensity. So the intensity is still low but considerably higher than what was in minima. Or I have 5 different points. So 5 different destructive interferences, but all are going to meet at one point. So one destructive interference was having low intensity, another one was having low intensity, low intensity, low intensity. They will all meet. The intensity will increase. So I can say that for secondary maxima, the path difference should be an odd multiple of lambda by 2. So path difference should be odd multiple of lambda by 2, or let me have it here, for secondary maxima, path difference Bn, which is equal to d sine theta n, is equal to an odd multiple of lambda by 2, that is n plus half lambda. Take n as 0, half lambda, odd multiple of lambda, and by 2. Take n is equal to 1, 1 plus half, 3 by 2, odd multiple of lambda, by 2, and so on. So what we have here, d sine theta n is n plus half lambda, is the condition for secondary maxima. Again I can have sine theta n equals to n plus half lambda by d, correct? And again if the angle is small, I can have theta n is equal to n plus half lambda by d. Theta n is equal to n plus half lambda by d. This is the condition for secondary maxima. Okay. Now one more thing we can find out is the width of central maxima. To find the width of central maxima, I am just considering this diagram, taking this triangle, suppose this from this triangle. I am erasing everything else of the diagram, just leaving that part there. From the center of our lens. Now, there was the lens. Let me have this lens only, nothing else. This is lens 2, L2. Okay. For this, what are we considering? We are considering that the focal length of the lens is small f. Okay. And the width of central maxima on any side, like the total width of central maxima will be equal to this plus this, top half and bottom half, but I am taking only one part to be x. So what I do, I find the value of x, then multiply it by 2, I get the width of central maximum, and for it let us have this to have a focal length of f. The lens is having a focal length of f. So what we get here, we get that tan theta is equal to x upon f. And if I am considering that this lens was very close to slit, very close to the slit, suppose slit was very close to it. So distance between this slit and screen was capital D. Distance between the slit and screen was capital D. So I will have it here, or I can have it to be like it is approximately equal to x upon capital D. Correct? And considering that the angle is very small, if theta is very small, what do I get? Then tan theta is approximately equal to sin theta. If you remember, for a very small angle, tan theta is approximately equal to sin theta is approximately equal to only theta. So we can have sin theta equals to x by d. If I am taking the first minima, no, it should be the position of first minima, then we are having the width of central maxima. Width will be the distance between the first minima down and the first minima up will be the central maxima, correct? So for first minima I am erasing this part and this part also. So for minima we had theta equal to n lambda by 2. So for first minima sin theta equals to lambda by small d. If I am taking this to be an equation, suppose equation number x I am taking it, I don't know which equation, and equation number y I am taking it. Comparing x and y, I get comparing x and y, I get x upon capital D is equal to lambda upon small d. Correct? Or x is equal to lambda into capital D upon small d. This is my value of x, that is one part. To find total width of central maxima I have to multiply it by 2. So I can write here width of central maximum can be given by 2x, which is equal to 2 lambda capital D by small d. So this is the width of central maximum. So this was all about diffraction. The video of today ends here. In the next video we will move forward. Please go through this video very carefully. If you are unable to understand something, give it one more shot. Even if there is problem, we will have the Zoom meeting in which we will discuss this in the doubt session. Thank you and have a wonderful day ahead.